All right, thank you, Chuck. Did I tell you he was good or what? That was a great presentation. Our next presenter is Bill Hay. I really have to say that Bill Hay is one of those people that seems to have been everywhere, done everything, and met everybody who's important in his field. He has an amazing career that spans many decades, and he's got a really impressive life history. Bill has a PhD in geology from Stanford. He is Professor Emeritus of Geological Sciences at University of Colorado Boulder. His research interests span everything from global paleoclimate modeling and verification to modeling tectonics to global carbon cycle. His recent publications, just since 1990, which is significantly less than half of his career, numbers over 90. His most recent publication is his new 1,000-page book called Experimenting on a Small Planet. If he has any copies left, I would recommend checking it out. I have a copy myself, and it's really excellent, and it's written for the lay audience, and it's very thorough. It covers a lot of different topics. So Bill Hay is our next presenter.
For some reason, my line about the Regional Climate Symposium got moved up here. I also set myself a little clock so I can keep track of what it was I was supposed to say. All right. Thank you. Thank you. I'm going to start with the very basics here. The Earth's energy balance. We receive insolation from the sun. Some of it's reflected back into space. That energy from the sun heats the planet. We have emission from the planet. And that emission from the planet is interfered with by greenhouse gases and clouds. Well, if we look at the history of the Earth has had what we call a greenhouse climate for most of the time. Greenhouse climate, in a greenhouse climate, you don't have an ice on either pole. There's another state that the Earth gets into every once in a while called an icehouse state, where it develops ice on one or both poles. The idea of having ice on both poles is pretty new. It just started about 35 million years ago. More than 500 million years ago, there were episodes in which greenhouse gases got very low and the Earth turned into a snowball. The Earth also has another state called the hothouse state. These hothouse states are extreme warmth, and you really don't want to go there. They last for less than 1 million years, and they're associated with very large injections of carbon dioxide into the atmosphere. Now, geologists call the last 1.8 million years the Quaternary, the last 11,000 years the Holocene, and the last 8,000 years the Anthropocene, because humans began to affect the climate 8,000 years ago, but civilization really began about, what we would call civilization began 6,000 years ago. Well, these are the climate states. Earth spends most of its time in the greenhouse state, about 18% of the time in the icehouse state. In the icehouse state, it oscillates between glacial episodes and interglacials. And we're living in one of the interglacials. The Earth spends only about 1% of its time in this particular condition. It really prefers the greenhouse state. Now, if you look at the past couple of million years, this is the normal state. And the white areas are ice. And you'll see that a large part of the northeastern part of the United States and most of Canada are covered by ice. This is the extreme state that it occasionally gets into, called a glacial maximum. This happened about 24,000 years ago, and the ice came down to the Ohio Valley and out here, we would have had continental ice extending out here to the edge of the Rockies. This is the interglacial state. The Earth spends very little of its time in this, only 10,000 years at a time, and that's what human civilization has developed in. Now, what can change the energy balance and cause these changes in the condition on the Earth? Well, changes the insolation from the sun, the albedo, reflectivity of the Earth, and greenhouse gases. These are the changes in insolation. These are changes due to variations in the orbit of the Earth around the sun. In the upper left, you see the changes in the ellipticity of the orbit. When we're closest to the sun, that's called caloric summer. Caloric summer now occurs on January the 4th. That's when we are closest to the sun. But in the northern hemisphere, we're tilted away from the sun. The diagram on the right shows the obliquity of the axis of rotation of the Earth, tilted about 24 degrees from the sun. So that occurs in the middle of winter. But what it means is that the insolation for the northern hemisphere is at a minimum during our summer and at a maximum during our winter. In the southern hemisphere, it's exactly the opposite. Now, the other thing that occurs, you'll notice the time scales that are on these. The ellipticity changes on a 100,000-year time scale, with a big cycle on 400,000 years. The obliquity changes on about a 40,000-year time scale. But the elliptical orbit precesses changing the date of caloric summer and winter on a roughly 24,000-year time scale. So when they say, well, it's changed in the past. Well, yes, on 10,000-year time scales, and all of human civilization has developed in the last 6,000 years. So we're talking about two very different things. Now there is also, I didn't put that in here, but there's also some solar variation with sunspots. And you may hear a lot about that. You have to realize that the notion that sunspots affected climate goes back to a German gentleman in the 17th century who had moved to England. He had lived near Frankfurt with the Rheingau just outside, and he was looking for some way to decide which Rhine wines would be the best, what would be the best years. And he tried to make a correlation with sunspot cycles. It didn't actually work, but the idea was picked up. And people have been looking for correlations with sunspot cycles ever since. And for example, the Titanic sank on a sunspot minimum. The Monica Lewinsky affair. So there are clear, obvious implications. Now, the albedo, if you look at the albedo, these are the ones that are associated with land. And you can see you can change things on land quite a lot, and not much happens. But these are the ones that are associated with snow and ice. And if you change those, you do change things a lot. There's clouds on there also, and water is shown over on the right. Water is very absorbent when the sunlight is coming down directly onto it. But if you get to high latitudes, the sunlight can glance off the water when the sun angle is about 20 degrees above the horizon, and the energy does not go into the water. Now, this is what the absorption of radiation by greenhouse gases look like. First of all, in the top of the diagram, you'll see the incoming radiation from the sun. The sun is 5,700 Kelvin temperature. It's pretty hot. The Earth is, what I put on there, 289 Kelvin, and that is the radiation back from the Earth. For the Earth to maintain a constant temperature, those two must be equal, and the Earth tries to keep them equal. The only way they can change is through the insulation from the orbital parameters, and over the course of years, they change very, very, very little. Now, there has been a long-term change because the sun was less bright early in its history than it is today, but that's a change on the order of billions of years. Now, down below, you see where these absorption lines are for greenhouse gases, and you'll see the bottom one, that's water vapor. That's spectacular. Water vapor is the major greenhouse gas. Unfortunately, though, for the climate denial communities, it's not evenly distributed. Water vapor content in the atmosphere depends on temperature, and it doubles or reduces by a factor of 2 with every 10 degrees Celsius temperature change. Now, if you remove, I've now put those radiation things in the background. We put all the greenhouse gases up there, and you'll see that water vapor has a big absorption effect on the outgoing radiation. Virtually nothing has any effect on the incoming radiation except ozone, which is intercepting, thank God, the ultraviolet. But now if you go to the polar region, the situation looks like this. And you see that the carbon dioxide is sitting squarely, just by chance, in the back radiation from the Earth. So in the polar regions, you expect a very big effect from changing carbon dioxide. In the lower latitudes, not so much. Without greenhouse gases, the Earth's average temperature would be minus 18.6 Celsius. That's 1.5 degrees Fahrenheit. Large areas would turn white, reflect sunlight. That would increase the albedo from its current value of 0.3 to 0.8. And that would cause the temperature to drop to minus 87 Celsius or minus 125 degrees Fahrenheit. And this did happen at least 3 times around 600 million years ago. But then, it's never happened since then, and that's because life forms have developed since then that prevent this from happening. This is the Earth and its atmosphere. This shows you where water vapor is distributed. Where it's there, you already have a large greenhouse effect, and increases in CO2 are not so obvious. But here's why CO2 is so important. It's evenly distributed. And so you expect to see large effects in the polar regions and much smaller effects where the H2O effect is large. So it's very effective in the polar regions and particularly in the Arctic because the Arctic Ocean ice is at sea level. Whereas Antarctica is at about 7,000 feet average elevation. So almost a third of the atmosphere is below the Antarctic continent. So a third of the CO2 is also missing down there. Now, you'll find in every textbook that deals with climate, you'll find a diagram that looks like this. And it shows you the 3 big atmospheric cells. They're not so obvious when you look from, satellite imagery unless you know what you're looking for. But they're quite obvious if you look at ocean currents because these winds drive the ocean currents. The ocean currents integrate the whole signal and they make the big gyres shown in blue here. The white is winds, the blue arrows are ocean currents. And we have what's called a Hadley cell that extends from the equator to about 30 degrees north, a Ferrel cell that extends, it's an intermediate cell that extends between 30 and 60, and a polar cell that extends from there to the pole. We say the two Hadley cell and polar cells, those 2 cells drive everything. The Ferrel cell is the intermediate cell, and it can wander back and forth with the seasons. Well, this diagram is wrong. Whoops, let's see here. What happened? There we go. Something is very wrong. For this to work, you have to have ice on both poles. And that ice essentially stabilizes the climate system. That's very important to know. Now, where are we? Well, up above it shows you the eccentricity changing through time, the 100,000-year cycles, and you'll notice that you're seeing the end of a 400,000-year cycle, and we're going down to an almost circular orbit 6,000 years in the future. Now, all 3 of the orbital motions are shown in the middle panel, combined, and you'll notice there is a depression there that I've labeled last glacial maximum. It actually precedes the glacial maximum because it takes time for the ice to build up. And then you'll see one that's labeled T1, that's called termination 1. That's the deglaciation after that glacial maximum, leading to the present day interglacial. And you'll notice, of course, it's a little offset The other thing you'll notice, the vertical dashed line there is the present. This also shows you the future, which can be calculated very well. And the bottom panel shows you the northern hemisphere ice volumes as they would be expected if it were a normal system. And here is the ice volume if we add CO2 into the system. Now, these interglacials, the deglaciations, an interglacial maximum, and then the rest of the interglacial look like this. I'm going to show you the last four. That's one that was 300 and something thousand years ago. This was one that was 200 and something thousand years ago. These are roughly 100,000 years apart. This is the next to last one. It looks very peculiar, and that's because the orbital parameters are a little peculiar then. But this is the one we live in, and you'll notice it's very different from the rest. You get to about, it goes over a, pardon me, goes over an interglacial peak about 8,000 years ago, and then that peak is low, and then it declines to 8,000 years ago, and then it starts up. And why did it do that? Because of the development of agriculture and the increase of carbon dioxide into the atmosphere by human activities. Clearing of forests to release carbon dioxide, the development of rice paddies to release methane, and the domestication of cattle also releasing methane. Now, the real problem with the Earth is population growth. And this is the Earth's population curve. You'll notice it's a semi-logarithmic plot. Those are millions on the left there. There are two depressions that are very interesting. One caused by the Black Plague, which was not just a European phenomenon, but also reduced the population of China, which was 200 million before the Black Plague and 100 million after the Black Plague 3 years later. And here's the smallpox epidemic introduced into the Americas, which probably killed off 90% or more of the Native American population. That's what the population looks like on an ordinary diagram, so you can't see anything there. The effect of reducing the population causes regrowth of forests over formerly cultivated land, and that draws down atmospheric CO2. Pardon me again. And the abandonment of rice paddies reduces the amount of CH4 into the atmosphere. Both result in cooling. Now here are diagrams that show you the northern hemisphere and the southern hemisphere. And the northern hemisphere, this is for the past 1,800 years. And you'll notice we have a thing called the medieval climate optimum. Then things declined after the Black Plague and the smallpox epidemic. And we had in the northern hemisphere what's called the Little Ice Age. None of this is quite so obvious in the southern hemisphere. And you'll notice in the southern hemisphere that the temperature just wanders all over the place. Now, what on earth is going on there? Well, that's a thing called the conditions in the Pacific. The upper right diagram shows the normal conditions in the Pacific. And then the lower two diagrams show you the variations that occur quite regularly on decadal timescales of El Nino and La Nina, the two conditions of upwelling and suppression of upwelling in the eastern Pacific. And notice the temperature scale down there. Those things have 8 degrees Celsius difference between them in the extreme parts. 8 degrees Celsius is about 15 degrees Fahrenheit. So that makes a very, very prominent variation that shows up in the southern hemisphere. And incidentally, things like our Dust Bowl, we have no idea at the time what was causing that. Those were caused by these southern hemisphere phenomena. Well, the northern hemisphere has its weak spot too, and that's in the North Atlantic, where there are a series of places where water sinks to form deep waters. And that's very important to know about, because that's how the CO2 that gets into the surface waters in the ocean gets down to the deep sea. These are the climatically sensitive areas here. Very big one in the southern hemisphere, a very small one in the northern hemisphere. And now we come to what has happened more recently, the Industrial Revolution, which has two competing effects, introducing CO2 into the air and aerosols into the air that reflect sunlight. Herman Flown, back in 1982, made the comment that long before global warming due to CO2 can be proven, its effect will be noticed by the extremes of weather, which you've just heard about, setting local records such as the highest and lowest temperatures, greatest and least rainfall, snowfall amounts, most powerful storms, unusually large numbers of tornadoes, etc. These indicate that the climate system is becoming unstable in response to the greenhouse effect. So we had two episodes, a period in which humans seemed to stabilize and produce the most stable climate the Earth has seen for at least 1 million years, from 4000 BC until 1775. And then our period of climate destabilization since the Industrial Revolution. This is the record of CO2 in the Vostok Antarctic ice core, and you can see the variation there. Now remember, glaciations and interglacials are not caused by CO2. That's a secondary effect. They're caused by insulation changes. This is what's happened since then. During the glacials and interglacials, it's about, 100 parts per million by volume. We've added in 125 parts per million by volume since the Industrial Revolution, most of it in the last few decades. The rate of change is about 300 times faster than the most rapid change in the past million years. I like to think of that in terms of the difference between what happens when you drive your automobile into a concrete pillar at 1 mile an hour, or if you were able to, hit the concrete tower at 300 miles per hour. The effects are different. This is the famous US view of the temperature record. I'm going to go a few minutes over here. As it looked in the 1970s, and if you put a curve through that, everybody thought, or at least geologists thought, we should be returning to an ice age. Insulation-wise, we should be returning to an ice age. And I'm going to skip this. Wally Broker had it all right. He said, this is caused by dust and other stuff, and we're going to come out of this pretty quickly, and we should see global warming from CO2 by the end of this century. So there it is. That's the US temperature record. Now, since 1990, this whole thing has gone, there's been a very, very strong acceleration, especially in the polar regions. You'll notice the temperature change is concentrated in the North Polar region. This shows you the sea surface temperature anomalies, and you can see that this was just a few weeks ago. The oceans are warming much more than one would hope. But here is what is really spectacular. The gray lines are all models for the amount of sea ice in the Arctic Ocean, 14 of them. And the red line is the actual data. And you'll notice that we are 70 years ahead of time in the in reality with the sea ice decline. This wasn't supposed to happen until the end of this century.